So a sequence is a list of numbers that are ordered and are related by some pattern. So for example, 2, 4, 6, 8, 10, this would be a list of even numbers that are patterned by adding 2 to each successive previous number. So a mathematical sequence is just a list of numbers that are ordered or connected by a pattern. For example, 2, 4, 6, 8, 10 are easily recognized as a sequence of even numbers. They're ordered by the pattern add 2, start with an even number, and then add 2 to each successive number in the sequence. So this can stop at any given point, at which case it would be called a finite sequence. Or it could go on 12, 14, 16, and on and on and on, because I obviously can't number all the way to infinity. And that would be, in that case, an infinite sequence. So the first step in understanding sequences is really starting to get a hold of how to find additional terms in a sequence. The word I just used, by the way, term, each element in a sequence, so each number, each successive number is called a term in the sequence. And so finding the next term in a sequence is often as simple as finding a pattern. For example, with even numbers, because I know the pattern of even numbers, I can always find the next term, 18, then the next term, 20, because I understand the pattern for skip counting even numbers. Sometimes the pattern isn't as clear, and it's helpful to write the sequence out. So for example, if I were given the sequence 3, -1, -5, -9, and asked to find the next term, I might see it in my head, but sometimes it's really helpful to move from one to the other to see if there's a pattern that emerges. So simplest of all would be 3. To move from 3 to -1 would have to subtract 4. Does that hold for the next term? Well, -1 minus 4 equals -5. -5 minus 4 equals -9. Now I can fill in the next 4 terms, because -9 take away 4, -13, take away 4 more, -17, take away 4 more, -21, take away 4 more, -25. So that one was pretty easy. But not always, patterns aren't always as straightforward as the one just shown. Another example would be to find the next 4 elements of 18, 15, 10, 3. And now I want to look at the pattern. Well, to go from 18 to 15, that would be take away 3. So 15 take away 3, I'm expecting a 12, but I don't get a 12. So I'm going to have to explore this a little farther. 15 take away 5 would be 10, and then 10 take away 7 would be 3. So it looks like each iteration is to take away consecutive odd numbers, meaning that the next would be 3 take away 9, so -6, and then -6 take away 11 would be -17, and -17 take away 13 would be -30, and so on. But if you look at this more closely, there's not really enough information to guarantee that that is the actual next few numbers in the series, because, excuse me, in the sequence, because 3, 5, 7 are also the first 3 prime numbers. So it could actually be that the next numbers are the next prime after 7 is 6, 7, 8, 9, 10, 11. So 3 take away 11 is -8. And then negative 8, take away the next prime number, negative 13, would be negative 21. And then the next prime number after 13, 14, 15, 16, 17, take away 17 would be negative 38, and could go on from there. So it's fair to say that a sequence is not really revealed with only a first few numbers. But at this stage of the game, we could have gone with either of those and you would have been considered correct had you found either of those or maybe another pattern. So a more useful or more valuable way to determine the elements or the terms of a sequence would be a formula. And it turns out for sequences, there are two types. One is called a recursive. And the recursive formula is designed to take you from a first element. I should tell you, I call this the element. Your text uses the word term. I will try to use term, but if I say element, I'm speaking about a term. So the recursive formula is designed to take you from a first term, say a sub 1, to the next term, which can take you to the next term, and then on and on and on to the next term. It's very similar to a formula that I might have used in the first example. And the other type of formula is called explicit. And an explicit formula, it doesn't matter what the first term is or the second or the third or any term. An explicit formula will take you right to the term you want to know. So you can go right to, if I want to know a sub 16, a formula, the explicit formula would take me right to a sub 16. So you can see that the explicit formula is likely to be the more powerful, which isn't to say recursive isn't important, just explicit can take you anywhere you want to go. So let's look at an example of each. So I want to do a recursive formula first. I'm given a sub 1 is 3, and I'm told that the formula to get me to a sub n equals 3 times a sub n minus 1. That means n minus 1 being the previous one, right? So if I want to get to this one, I have to know the n minus 1 term first. Let me finish the formula. Minus n plus 2. Okay, so I'm going to write this a slightly different way. Instead of just writing it as a sequence, I'm going to write it out as a bunch of calculations. So I know that a sub 1 equals 3. A sub 2 equals a sub 1, right? 3 times a sub 1, so a sub n minus 1. If n is 2, then n minus 1 is 1. So that's 3 times 3 minus n is 2 plus 2. And so the second term is 9 minus 2 is 7 plus 2 is 9. Or I guess I could have just called that 0. So now a sub 3 is 3 times 3 minus 1. So a sub 3 minus 1 is a sub 2, and its value is 9, minus n, which is 3, plus 2. So that's 9 times 3 is 27, minus 3 plus 2 is minus 1, 27, take away 1, 26. A sub 4 is 3 times a sub 4 minus 1 is a sub 3, and the value for a sub 3 is 26, minus n, which is 4, plus 2. So that's 26 times 3 is 60, 78, take away 2, 76. So let's try to do a sub 5. A sub 5, we're going to skip, we're going to skip a sub 5, and let's try to do a sub 6. So that's 3 times a sub 6 minus 1 is a sub 5, minus n is 6, plus 2. So notice what happened. I'm able to put in my n value because my sub value, my n value is 6, but I need to know what a sub 5 is in order to complete the next term or to calculate the next term. So in a recursive formula, I have to know every term on the path to the term I want. So you can see if I wanted the 100th term, I got a lot of calculations in my future. And in that case, we would prefer an explicit formula. So let's look at one of those. Let's find the first 4 and the 16th term of the formula of the sequence given by the formula a sub n equals n cubed plus 1. So the first 4 means I want to find a sub 1, a sub 2, a sub 3, and a sub 4. And then what did I say? A sub 16? All right, so a sub 1, n cubed, and in this case n is 1, so 1 cubed plus 1 equals 2. A sub 2, n in this case is 2, 2 cubed plus 1, 2 cubed is 8 plus 1 is 9. A sub 3, 3 cubed, because 3 is n, is 27 plus 1, 28. And the fourth element is 4 cubed plus 1 equals 64 plus 1 is 65. So the 16th element then, n is 16, that's 16 cubed plus 1. I'm not going to do that arithmetic. The important thing is to notice that the value of this element is not dependent on knowing a sub 5, 6, 7, 8, 9, all the way up to a sub 15. I don't need to know the previous element. So it's possible to consider a sequence an input-output set of values. So if I were to, let's look at this third example here. If I were to consider the horizontal axis to be n, meaning which iteration am I talking about, I could label it with 1, 2, 3, 4, and so on. And then the value of each iteration or each element could be graphed on the y-axis. And so if I plotted 1 to 3, a sub 2 is equal to 9, a sub 3 is equal to 26, a sub 4 is equal to 76, which is way off the table. I'm not going to connect these because they're not functions, they're discrete elements, but you can see that if you imagined they were connected by some kind of a curve, the curve would go off to infinity, and we're used to considering that. Well, we say the same thing about the series of points. They seem to be headed off to values approaching infinity. So when points of a sequence take this kind of going off toward some other bigger and bigger value, it could happen in the opposite direction, but if they take off in greater value, then we call this divergent. So they diverge. The points move away from the x-axis or the n-axis. Another way that the points may behave is on n. They may kind of bounce around a bit. So maybe they're up. The first point is up here, and the second point is kind of here, and the third point is kind of here, and then the fourth point is kind of here, and they might bounce back and forth, but notice how they seem to be converging towards some point. If they were graphed or connected, they would just look like zigzags, but the zigzag would be looking like it's going to head off toward a particular line or a particular spot in space. When this happens, we call this convergent, because the points converge toward a single value. And the last thing that can happen is a sequence can kind of bounce around and not really take off toward anywhere or converge closer and closer to something. The values just sort of bounce around, you know, maybe getting a little bit farther and then a little bit closer, but they never seem to be getting closer and closer and closer to a point or some value, or they never seem to be taking off toward positive or negative infinity. In this case, we actually call this also divergent. So when we're classifying a sequence based on the appearance of its graph, we either have a convergent sequence or we have a divergent sequence. That's the only option. If it doesn't converge, then it diverges. Well, it looks like my time is up. I didn't get a chance to talk about series, so I'll continue that on the next lesson.